Greetings, my name is Edgar Gabriel Poesina, and I'm a PhD student from the University of Bucharest, Romania. And I'm excited to present our survey on text classification on the class distribution shift. This is a joint work with my PhD colleagues Adriana Costache and Silviu Gheorghe, and Professors Paul Irofti and Radu Ionescu. Our work addresses a critical gap in NLP research. While class distribution shift has been extensively studied in computer vision, it remains comparatively underexplored in the text domain, and our survey aims to bridge this gap. Let me explain the core problem using this illustration. In text classification, we can divide classes into four categories. KKCs, which are known classes, are used in standard supervised learning scenarios where you have labeled training data. KUCs, which are known unknown classes, represent available background data but without specific labels. UKCs are known classes, are classes you know that exist but you don't have examples for. This is where zero-shot learning comes in. Finally, UUCs, unknown classes, are completely unknown during training and appear only at test time. The key insight here is that the latter task, which we call open set learning and discovery, allows models to continuously adapt as new classes emerge in an unsupervised way. Why does this matter? Well, let me give you some real-world examples. The COVID-19 pandemic is a perfect case. Journalists started publishing articles about it only after December 2019. If you trained the news classifier before that date, it would have no category for pandemic-related articles and would misclassify them. Similarly, in authorship identification, new authors constantly emerge. In chatbots, users have new intents that weren't anticipated during training. The fundamental assumption of machine learning that training and test data are independently and identically distributed simply doesn't hold in these scenarios. In this survey, we propose a unified mathematical framework that connects the three learning paradigms that were previously treated separately: learning with Universum, zero-shot learning, and open set learning. Second, we formalize optimization objectives for each learning paradigm using a consistent notation system based on four class categories. Third, and perhaps the most important, we identify continual learning as the key pathway toward achieving the true open set learning and discovery in text classification. These contributions provide a comprehensive overview of the field and a roadmap for future research. Now let me show you our unified mathematical framework. This single equation connects all three learning paradigms. L joined equals LKKC plus alpha times LKUC plus beta times LUKC plus gamma times LUUC. What's powerful here is that by controlling these three scalar values, alpha, beta, and gamma, we can switch between different learning tasks. While these problems are fundamentally different, they can also be seen as a special case of a more general learning under class distribution shift problems. Let's break down each component. LKKC is a standard supervised cross-entropy, nothing new here. LQC uses a binary cross-entropy to distinguish between known classes and background data. LUKC employs contrastive learning with the class prototypes for zero-shot scenarios. This is where semantic similarity becomes crucial. Finally, LUUC is the most complex of them. It's supervised cross-entropy, where the class set UUC is discovered during inference via both outlier detection and clustering. This last component is what enables true open set discovery, not just detection. Here's how we activate each learning framework. For the Universum learning with background class, we set alpha greater than 0, while beta and gamma are 0. For zero-shot learning, we set beta greater than 0 while alpha and gamma are 0, and for open set learning, gamma is greater than 0 while alpha and beta are set to 0. This mathematical formulation makes it clear that these are complementary approaches, not competing ones, and suggests that future work should explore hybrid approaches that combine multiple paradigms simultaneously. Let's dive into the first paradigm, learning with background class. This can be addressed through proxy tasks like out-of-distribution detection or outlier detection. Distance-based and confidence methods are commonly used to distinguish between known classes and background data. However, here's a critical point. This area has received very little attention in NLP and text classification as opposed to computer vision. This represents a significant research opportunity, as many techniques from vision could be adapted for text by simply replacing image encoders with, for example, language models. The three most important works in this area are, first, Liu et al. On energy-based out-of-distribution detection, which introduces a novel loss function that creates clear energy-based separation between in-distribution and out-of-distribution samples. Second, Hendricks et al. On outlier exposure, which trains model on auxiliary out-of-distribution datasets. This is perhaps the most widely adopted approach. Third, Damija et al. On reducing network agnostophobia, introducing two complementary loss functions, entropic open set loss and objectosphere loss. What's notable is that all three focus on novel loss functions, suggesting that better optimization objectives are the key to this problem. Moving to zero-shot learning. This paradigm uses transfer learning to classify samples from unknown known classes. The foundational approach by Yin et al. Uses entailment to classify a text into a class. You basically check if it entails. This text is about that class. The simple idea underlies how modern LLMs perform zero-shot classification. A less demanding variant permits unlabeled in-domain examples. Importantly, zero-shot learning is widely studied in NLP, much more so than learning with a background class. However, this has a foundational limitation. It cannot handle unknown classes, because that class must be set fixed before inference. Three key papers define zero-shot learning in NLP. First, Yin et al., which introduced the entailment-based approach that became foundational for the field. Second, we have instruction tuning papers by Sun and Wei in 2022, which showed that training on diverse tasks enables zero-shot generalization. This scaled from dozens to over 1,000 tasks. Third, syntactic data generation by Meng and Ye showed that LLMs can generate training data for zero-shot scenarios. The progression here is clear. From entailment to instruction to synthetic data, each building on semantic transfer but increasingly sophisticated ways. Now we reach open set learning, which is the most challenging paradigm. Traditional open set learning just detects samples that don't belong to the known classes, using confidence threshold or distance metrics. But open set learning and discovery goes further. It must automatically discover new classes in the open space and ensure semantic alignment with existing classes. This is a novel task that has never been explored in NLP before. The key challenge is semantic consistency. When your known classes are sports, politics, economics, discovering culture kind of makes sense, but discovering breaking news does not, even though both might appear in open space. Now, three fundamental works in open set learning. First, Shirer et al. This is the foundation paper that defined open set risk and formalized the problem. Second, Chen et al. Introduced open set semi-supervised text classification specifically for NLP, relaxing the closed word assumption. Third, Volkoviak et al. Showed how to use local outlier factor for text, avoiding arbitrary thresholds through density-based detection. Notice these are much more recent than the foundational work. OpenSet is still an emerging area in text with much room for innovation. Let's compare these three frameworks directly. Looking at the table, we can see that each has different strengths and limitations. Universum can detect out-of-distribution data, but requires out-of-distribution training data and cannot classify it. Zero Shot can classify OOD data, but it cannot detect it and requires a fixed class set. OpenSet can both detect and classify OOD data with an unbounded class set, but it's very hard to optimize. The key insight from our survey is that no single approach solves all the problems, which is why we advocate for continual learning as an integrative solution. Know that OpenSet is the only framework that truly embraces the open world assumption. Let me quickly highlight the most commonly used dataset. AG News and DBpedia are used across all three paradigms. They're the workhorses of this research area with 127K and 630K samples respectively. 20 News Group is popular for Zero Shot and OpenSet, but not continual learning. Notice that most dataset involve topic categorization tasks. An important observation, these datasets don't always reflect real-world OpenSet scenarios because they were originally designed for closed-world classification. This suggests that collecting new benchmarks specifically for OpenSet scenarios is an important direction for future work. So, where do we go from here? We argue that continual learning is the most promising path forward. Let me explain the four key approaches. Disentanglement separates stable knowledge from task-specific adaptations. This prevents catastrophic forgetting while enabling adaptation. Memory replay generates samples from past tasks without storing large datasets. Adaptive prompting extends vocabulary dynamically as new classes emerge, inspired by the recent work in vision. And LLM integration can generate semantic labels for discovered clusters and provide confidence signal. The key insight is that continual learning enables simultaneously discovery, classification, and adaptation, the three requirements for true open-world NLP systems. Now, our GitHub repository contains a great list of all the surveyed papers. We welcome any questions. I will be happy to discuss any aspect of the survey. Thank you for your attention and feel free to contact us via email or visit our GitHub for the complete paper list. Thank you.